This section of the course is called dimensional analysis. Now, we've actually already used some of the results of dimensional analysis in earlier parts of the course, and I'm going to be pointing some of those out in my introductory lecture here. But the big reason we're looking at dimensional analysis is because it's very important in working with turbo machinery, which is the last section of the course. It's also important in many other applications in fluid mechanics that you might take in later courses as well. So what is dimensional analysis? Well, dimensional analysis is a method for representing phenomena that depend on many variables in a much more compact form. So take as an example the drag force on an object. And we're going to be talking about that example quite a few times here as we go through the introduction and the rest of this module in the course. So drag force on an object. And it could be a car, it could be an airplane wing, it could be a raindrop falling through the sky. So the drag force on an object depends on many things. The density of the fluid, the viscosity of the fluid, the velocity it's moving at, all kinds of geometric details of the object itself, its dimensions, surface roughness. So we could sit down and list many, many variables that drag force depends on. So that's a very daunting task to figure out how each of those variables influences the drag force. How does the drag force depend on the air velocity? How does it depend on the density? How does it depend on the viscosity? Investigating each one of these separately is a very, very large task. So in situations like that, fluid mechanics and other fields of study as well make use of something called dimensional analysis to try and simplify the problem. So to try represent the important features of a phenomena in a much more compact way. So the context that we're going to be looking at dimensional analysis in is very much experimental fluid mechanics. That's going to be our main focus. But if we were looking more into the theory, more into the governing equations of fluid mechanics, we would see that dimensional analysis is also important in theoretical analysis. We can take quite complex equations and use dimensional analysis to identify the important parts of those equations. So we're not going to be doing that in this class, though. We're going to be focusing on experimental fluid mechanics. How can we use dimensional analysis to do more effective experiments and to present the results of our experiments in a compact and useful way? So for experimental studies, that's exactly what dimensional analysis does for us. It allows us to identify so-called dimensionless groups. So all of those properties I listed, density, air velocity, dimensions of the object, surface roughness, all of those things. We can identify groupings of all of those things that are important in a problem. And that can greatly reduce the number of variables that we need to look at. So dimensional groups allow us to do three things, and we're going to consider each of these three things in this introductory lecture. First of all, we can show experimental results in a much more compact and useful form. And we may not have realized it, but we've already been making use of this particular aspect of dimensional analysis in the course so far. And I'm going to use an illustration from something we talked about in the last module to highlight this. The second thing that dimensional analysis can help us do is design much more efficient experiments. And by that I mean experiments where we can spend our time investigating the phenomena that are important instead of investigating a very, very long list of things that don't have very much influence on whatever it is we're studying. The third and final thing that we'll use dimensional analysis for is scale model studies, or determining the behavior of a large system by studying a small system. And the classic example of that in fluid mechanics is building a small model of an airplane or a car or a baseball or a hat or a bicycle helmet or whatever, and putting it in the wind tunnel and measuring the forces on it, and from the forces you measure in the wind tunnel, figuring out what the forces would be on the full-scale object. And there's lots of other examples of scale model studies in fluid mechanics as well. So those are the three things we're going to look at in the rest of this introductory lecture. How to show experimental results in a compact form, how to design efficient experiments, and how to do scale model studying. Now, we're not going to go into huge detail on all of those, but we're going to just introduce these three particular uses of dimensional analysis before we go into some of the details about how to do it. So the first example I want to look at is relevant to this first point here, showing experimental results in a more compact form. So the thing that we're going to use to illustrate how to present experimental results compactly using dimensional analysis is minor loss coefficients. Now, we used minor loss coefficients in the last section of the course to calculate the pressure loss through a fitting. So elbows, T's, valves, that sort of thing. So we took a minor loss coefficient, which we probably would have looked up in a table or perhaps on a manufacturer's data sheet, multiplied by the dynamic pressure, rho v squared over 2, and that told us the pressure loss, the minor pressure loss through that particular fitting. So there we were using minor loss coefficients that someone else had determined. Well, how was that minor loss coefficient determined? Well, almost exclusively, minor loss coefficients are determined through experimental measurements. So whoever designed that fitting takes it and pumps fluid through it at particular velocities, measures the pressure drop through it, and experimentally determines what this minor loss coefficient is so that others can use it when they're using that particular fitting. Now, the thing we need to realize is that minor loss coefficient is basically a dimensionless number. Remember when we were using them, we said they had no units. Well, it is a dimensionless number. So a minor loss coefficient is really a dimensionless pressure drop. So we can rearrange this equation, and the minor loss coefficient is the pressure drop due to the minor loss divided by rho v squared over 2. And of course, the numerator and the denominator have the same units. So this is called a dimensionless group. It's a particular grouping of parameters, a pressure, a density, and a velocity, a particular grouping that has no dimensions. Another way to look at it is all of the units cancel out. So Km is a dimensionless number, and it's a dimensionless pressure drop, essentially. So minor loss coefficient we can think of as a dimensionless pressure drop. So in our dimensional analysis section of the course here, this is our first dimensionless group that we're introducing. Well, let's take a look at why it's such a good idea to represent minor losses as a dimensionless group like this. So as an example, if we take a 90-degree regular flanged elbow and we look in our textbook, happens to be a 2-inch elbow, table 6.5 tells us that the minor loss coefficient for that elbow is 0.39. Well, realize that that same value of K works over a very wide range of density and velocity. Why do I say density and velocity here? Well, remember, those are the other two parameters that we need to know to take our minor loss coefficient and use it to calculate a pressure drop. Okay? So this is basically a very compact way to represent the experimental results that would have been acquired when they were taking pressure drop measurements through this particular elbow. Because what is the alternative? Well, just going back here a second, realize that the pressure loss depends on more than the minor loss coefficient, right? It also depends on rho and v squared. So let's say the manufacturer of this elbow wanted to present pressure drop information to their customers, which they certainly must do, and they didn't want to bother using minor loss coefficient. They kind of didn't understand that and didn't want to go that way. They thought, well, here was what we'll do. We'll just provide a table, and they can actually look up the pressure drop directly in kilopascals or pascals or whatever we specify as a function of density and velocity. Because we know the pressure drop depends on density and velocity, so we're going to have to provide them with tabular information or maybe graphs of some kind to give them pressure drop directly. Okay, so a single Km actually replaces all of that stuff, because if you look over a wide range of rho and v, delta P certainly changes, but Km does not. Okay, so a very compact way to represent a whole bunch of experimental results is just to give this single value for Km, 0.39. And you can use that no matter what fluid you're pumping through, in other words, different densities, and no matter how fast you're pumping it through the elbow, in other words, different velocities. You don't have to go look up a different pressure drop every time you change those parameters. You calculate the pressure drop from a constant value of Km. So this is an extremely compact way to represent experimental results. Now, being able to take advantage of that depended on us identifying that this is an effective dimensionless group in doing that. So that's part of dimensional analysis, is the process of coming up with this particular combination of things that happens to be dimensionless, first of all, and also happens to be constant over a wide range of conditions, making it so useful. So that's an example of how we can produce or how we can represent experimental results in a very compact way through dimensional analysis. Now, the second example I'll give is another one that should be familiar to you from one of the labs that you did a little while ago, and that's the Pelton wheel. So you'll remember the Pelton wheel lab. We have a rotating wheel here with a bunch of cups on it, and there's a jet of water hitting those cups and producing a torque. So the wheel rotates and does some work for us. So you took some data on the Pelton wheel, and if we plotted our raw data, or I'll call it our dimensional data, it would look something like this. Okay, so what do we have? Well, on the vertical axis, we have the power in kilowatts that the Pelton wheel is developing. On the horizontal axis, we have the rotational speed, so how fast it's turning. And each one of these families of curves on here is a separate jet exit velocity. So we've done a whole bunch of experiments here. We've varied the jet exit velocity. Apparently here we have 4 different jet exit velocities. There's 4 different colors there. And for each jet exit velocity, we varied the rotational speed. So there's quite a few measurements of rotational speed there, 8 or 10 for each jet velocity. And then we measured the power output for each of those. So we got a relatively large data set here. And we notice for each jet exit velocity, the curve looks a little bit different. As the jet exit velocity gets bigger, of course, the power output goes up. So the thing about this plot, let's say we were just to stop here and say, well, here is our set of experimental results. If you want to know how this particular Pelton wheel behaves, this is what you need to look at. Well, that's all well and good for this particular Pelton wheel, but what if we wanted to look at a Pelton wheel that was of the same general design but was bigger or smaller? Or we wanted to look at some operating conditions that we hadn't specifically looked at here, maybe a different jet exit velocity or something. Well, if we represent these results in a non-dimensional form using dimensional analysis, we get a much more useful plot than this that we can use over a much wider range of conditions. So let's see if we take this data and instead plot the efficiency of the Pelton wheel versus the cup speed ratio. Well, the first thing we want to emphasize here is that these two axes that I've replotted the data using, those are both dimensionless groups, right? Cup speed ratio. What is that? Well, that's the ratio of the speed the cup is moving divided by the speed of the jet of water hitting it. So those are both speeds, meters per second probably, and so their ratio is a dimensionless group. So cup speed ratio is a dimensionless group. Likewise, the efficiency of the Pelton wheel. So this is the ratio of the power it actually develops, so the shaft power, torque times omega that is being delivered by the shaft, divided by the kinetic energy in the jet of water hitting it. So that's a ratio of 2 powers. So that also is a dimensionless group. In fact, all of these efficiencies that we talk about in engineering, they're really dimensionless groups because they're unitless numbers. They're usually expressed as a percentage, but they're a ratio of 2 powers or a ratio of 2 energies or something like that, okay? So they're always dimensionless numbers. So think of efficiency as dimensionless power and cup speed ratio as dimensionless speed. Well, when we take that exact same set of data on the previous slide and replot it using cup speed ratio and efficiency instead, all of the data so-called collapses to the same curve when it's properly non-dimensionalized. In other words, when we've chosen the right representation of the rotational speed and the right representation of the power developed in a non-dimensional sense. So coming up with the expression for the efficiency and coming up with the cup speed ratio as being an important parameter, that's what dimensional analysis will do for us. And once we've done that dimensional analysis properly, this shows us that actually there's just a single curve that represents the characteristics of this particular Pelton wheel. And that's much more useful in predicting the performance of other similar Pelton wheels. Pelton wheels that are constructed the same, but maybe are larger or smaller or are running at a different speed or with a different jet velocity. Just this single curve that we have here gives us all that information. Whereas if we represented these results dimensionally, like we did on the last slide, it's much harder to use that in other applications or in other situations. So these two things, the Pelton wheel data and the minor loss coefficient, have illustrated sort of the first use for dimensional analysis, and that is representing experiments in a compact way. The second thing that we might use dimensional analysis for is experimental design. And I'm not going to spend nearly as much time on this, but I am going to talk about the Darcy-Weisbach equation, which again we used in our pipe flow section of the course. And I'm going to use this as an example of experimental design. Well, remember this F is so-called friction factor. Well, realize friction factor is a dimensionless pressure drop. Now, I haven't written it like this, but we could take delta PF and divide by all of this stuff, and we would get our expression for F, right? And that has the units of pressure, and all of this has the units of pressure, so F is a dimensionless number. So F is also a dimensionless number. And how is it defined? Well, it's defined as delta P due to friction divided by L over D rho V squared over 2. So it's a particular combination of these parameters that forms a dimensionless number. Well, if we're trying to do experiments to figure out what the friction factor is in a pipe, remember the pressure drop in a pipe depends on a lot of things. It depends on the length of the pipe, it depends on the diameter of the pipe, it depends on the density, it depends on the velocity, it also depends on the viscosity of the fluid and the roughness in the pipe. So there's quite a long list of parameters that the pressure drop depends on. And so if we were to ignore this friction factor and try to write an expression for delta P friction as a function of all of those parameters, it'd be a very complicated expression. Okay? So instead, we do dimensional analysis, and dimensional analysis will identify this friction factor, or this ratio of the pressure drop divided by L over D rho V squared over 2 as an important parameter. And further, it will also tell us that that friction factor can be written as a function of only two things, Reynolds number and relative roughness. And in the last section of the course, we took what Reynolds number and relative roughness is, but realize those also are dimensionless groups. Reynolds number is density times velocity times diameter divided by the dynamic viscosity. And if you look at the units of all those things, the Reynolds number doesn't have any units. It's a dimensionless number. Likewise, our relative roughness, epsilon over d, is also a dimensionless number because this is a length and that's a length. So epsilon over d doesn't have any units. So when we go to do experiments, let's say we were trying to do a series of experiments to determine what friction factor is. The reason that this dimensional analysis is so useful to us is we now know that friction factor only depends on these two things. So we can just vary these two things to investigate what friction factor looks like. Okay, so if we were going to do experiments here, we're trying to figure out what does this function look like? How does F depend on these parameters? Well, that's a lot easier process to do once we've determined that there's only two parameters here instead of 6 or 8 or however many there would be. Okay, so much more efficient experimental design because we can then do our experiments much more quickly. We only need to vary 2 or 3 parameters, dimensionless parameters, rather than varying 7 or 8 parameters. So that's our second very useful application of dimensional analysis, is guiding experiments, making experiments much more efficient by reducing the number of measurements we need to make to investigate a particular phenomenon. So the third and final application of dimensional analysis that we listed earlier is scale modeling. So scale modeling relies on geometric similarity. So what do we mean by geometric similarity? Well, if we have a model, and here's a little sketch of a car, there are a whole bunch of dimensions that we could list for that model. Here I've just listed the length of the model and the height of the model. So we want to get used to the notation here. The subscript m here refers to the model, which presumably is a smaller scale. Well, the prototype, which is the full-scale car in this case, also has a length and a height, and we have the subscript p here to represent the fact we're talking about the prototype here. Well, geometric similarity, which is what we're talking about here, geometric similarity between these things is achieved if the ratio between the model and the prototype of any dimension is constant. Okay, so the ratio of the length of the model to the length of the prototype equals the ratio of the height of the model to the height of the prototype equals any other dimensions of the model and prototype that we want to list here. So how big the mirror is sticking out the side, how big the door handle is, how big the headlights are, everything has to be in exactly the same ratio between the model and the prototype, and then those objects are said to be geometrically similar. Okay, so sometimes this is a little bit difficult to achieve. The very, very small details sometimes are hard to scale. So things like surface roughness or very, very fine details on a large scale object, when you shrink it down to a model to put in a wind tunnel, sometimes it's really hard to achieve those small details, but hopefully those small details aren't that important in the results quite often. So how does scale modeling work? Well, scale modeling works because it is much, much easier to make measurements on this model than it is to make measurements on the prototype. First of all, we don't need to build the large-scale prototype, which might be a very expensive thing to build. We can build a much cheaper model. So just the construction of the object is much, much simpler when it's smaller. And secondly, the measurements are much easier to do. You don't need a monstrous wind tunnel. You don't need the ability to measure very, very large forces on the object. A relatively small wind tunnel and an ability to measure moderate forces is just fine. Now, measuring forces on a small-scale model like this, though, doesn't do you any good unless you can use the results that you got on the small-scale model and predict what the forces are going to be on the large-scale model. And that's where dimensional analysis comes in. It allows us to take measurements made at one scale and figure out what those measurements would have been if we made them at full scale. So that's scale modeling. And this is a part of dimensional analysis that we use a lot in the turbo machinery section of the course, because there we're going to talk about pump scaling laws. If you have a pump designed with a certain impeller characteristics, the diameter of the impeller, the pitch of the blades, and all those kinds of things, and you scale that pump up or down, how are its characteristics going to change? That's a very important part of the turbomachinery section of the course. Well, that's a scale modeling issue. So we're going to investigate scale modeling in the dimensional analysis section of the course here, and we'll be using it a lot in the turbomachinery section of the course. So that's the end of our introduction to dimensional analysis. So remember, there's three things that it can be used for: to represent experimental results in a compact way, to guide experiments and do them efficiently, and to take experimental results measured at one scale and predict what those results would be if you had done them at a different scale, so-called scale modeling. So in the next lecture, we're going to look at a couple of other types of similarity beyond just geometric similarity, and that'll prepare us to learn the technique used to form these dimensionless groups. So we'll see you in the next video.